Say you've built a CFD model of a patient's pulmonary arteries. You're after the things a scan can never hand you, where the flow claws hardest at the vessel wall, how much energy it burns on the way through, the load it puts on the right ventricle. But a simulation is only as honest as its boundary conditions. And at every outlet where the blood leaves your model sits a question mark. Before any of those numbers mean a thing, we have to answer it, and then earn the right to believe the result. One quick note on what you're actually looking at. To keep this simulation fast enough to run live, the artery here is an idealized two-dimensional model, a main pulmonary artery splitting into its left and right branches. Nothing about the method leans on that shortcut. The way we tune the Windkessel and validate it is exactly the same for a real, three-dimensional patient scan. The geometry is a stand-in, the procedure is the real thing. Here's the trouble. You can image the big arteries, the ones with a luminous scanner can resolve. But past each outlet the vessel keeps branching, smaller and smaller, into millions of arterioles you will never mesh. And that hidden forest is exactly what sets the pressure your model feels. You can't simulate it directly, so you do the next best thing. You replace the whole downstream tree with a small model that behaves right at the outlet, the way the real tree would. That stand-in is the Windkessel. Windkessel is German for air chamber, and it comes from old fire engines. The pump throws water in hard pulses, but you want a smooth stream at the nozzle, so you route it through a sealed chamber with a cushion of air on top. The air compresses on each pulse and pushes back between them, and the flow leaves steady. Your arteries do the very same thing. The heart ejects in sharp beats, the big elastic arteries balloon to store that blood, then squeeze it back out through the small vessels during the lull. So the simplest model has two parts, something that stores, a compliance, and something that resists, a resistance. That two-element version is close, but it has a flaw right where the blood enters. The incoming pressure wave hits the model and, with nothing to absorb it, partly bounces back. The model reflects energy, the real artery wouldn't. The solution is a third element, a small resistance in series at the inlet, sized to match the artery so the wave slides in cleanly instead of echoing. That matching value is the characteristic impedance. Add it, and you have the three-element Windkessel, a proximal resistance in series, then a compliance and a distal resistance in parallel. 3 numbers per outlet. So where does the Windkessel equation actually come from? Just 2 laws apply to this circuit. Call the pressure the CFD outlet feels P in, and the pressure at the node just past the proximal resistance, P. The first law is Ohm's law across that resistance. The pressure it drops equals the flow times its resistance. So P in equals P plus Q times the proximal resistance. The second law is conservation. The flow arriving at the node splits between the 2 elements it meets. Some of it charges the compliance, the rest passes through the distal resistance. Now name those 2 currents. The current into the compliance is its size times how fast the pressure is rising. The current through the distal resistance is just ohm again, pressure over that resistance. Together, the flow at the node is compliance times the rate of change of pressure, plus pressure over the distal resistance. Now fold in the first law. The node pressure is P in minus Q times the proximal resistance, so substitute that in everywhere. Expand the derivative, group the flow terms and the pressure terms, and you land on this, the 3-element Windkessel equation. Compliance times the rate of change of the outlet pressure, plus pressure over the distal resistance, equals the flow times 1 plus the resistance ratio, plus compliance times the proximal resistance times the rate of change of the flow. That's what each outlet integrates every time step. Now what those 3 numbers actually do, because each owns a different piece of the pressure. The distal resistance is the small vessel's resistance to steady flow. It sets the mean, the average pressure is just that total resistance times the average flow. The compliance is the elastic storage, the cushion. It sets the pulse. A stiffer artery, a smaller cushion, and the pressure swings wider and drains faster between beats. And the proximal resistance, the characteristic impedance, is density times wave speed over the artery's area. It catches the very first instant of each beat, the steepness of the upstroke, mean, pulse, upstroke, 3 features, 3 knobs. One more view of the same equation. Drive the model with a steady oscillation, and every rate of change becomes a simple multiply. The equation turns purely algebraic. Solve for the ratio of pressure to flow, the impedance, and it drops right out, the proximal resistance, plus the distal resistance divided by 1 plus the frequency term. That's the whole model in the frequency domain. There's an elegant way to see all three at once. Push the model with flow at some frequency and ask how much pressure comes back. That ratio is the impedance. At zero frequency, steady flow, the capacitor does nothing, and you feel both resistances in series, the total, proximal, plus distal. Now crank the frequency way up. The capacitor turns into a short, it hides the distal resistance, and all that's left is the proximal one, the characteristic impedance. The bend between those two limits sits at 1 over the distal resistance times compliance. Steady level, fast transients, and the corner in between, the same three numbers seen as three regimes. Two things are pinned before you tune anything. The inflow waveform is prescribed straight from phase contrast MRI, that's what's genuinely entering the artery. And the proximal resistance is fixed from anatomy, that density times wave speed formula. Leave it free, and a 3-parameter fit will happily drift it somewhere non-physical. Nail it down, and you're left tuning just two things, the distal resistance and the compliance. But a real geometry has more than one outlet. The pulmonary artery splits to the left and right lungs, and each branch needs its own 3 numbers. You don't start from scratch for each, you split the totals by how much flow each branch carries. A branch taking a bigger share gets proportionally less resistance and more compliance. Resistance divides by the flow fraction, compliance multiplies by it. The MRI hands you those fractions directly. One set of totals fans out into a triple at every outlet. Now the rule that keeps the whole thing honest. You tune the model using only non-invasive data. An echo gives a pressure anchor and a stroke volume. The MRI gives the inflow, the left-right split, and how the artery swells. The catheter, the gold standard right heart pressure, you deliberately set aside. Because if you tune to it, then matching it later proves nothing. It's circular. The catheter isn't an input, it's the exam you sit at the very end. You do need somewhere to start. A first guess for the compliance is the stroke volume over the pulse pressure, how much the arteries swell for a given squeeze. But treat it as a rough sketch, not the answer. That formula quietly assumes no blood runs off downstream during the beat, and in reality plenty does, so the true Windkessel compliance is smaller, sometimes several times smaller. The starting numbers get you close, the tuning is what makes them the patience. Now the loop. Run the coupled simulation once, then compare what it produced against the non-invasive data, 1 check per knob. First, the flow split. Say the model sends 62% to the left lung, but the MRI says 55%. The split is set by the ratio of the branch resistances, so raise the distal resistance on the branch that's hogging the flow, and rerun. Second, the pressure level. The simulated systolic pressure comes out at 55. The echo anchor says 65, so raise the total distal resistance until it lands. Third, the pulse. The swing is too small, 20 against the echo's 33, so lower the compliance. Because each knob barely disturbs the others, 3 or 4 passes and everything matches at once. There's a subtlety hiding in that pressure check, and it's why we needed the echo at all. When you prescribe the inflow, the flow field depends only on the ratios of the resistances, not their absolute size. Double every resistance and the streamlines don't move, only the pressure scales up. So the flow data pins the split and the waveform shapes, but it can't set the absolute pressure level. Something has to fix the scale. One pressure number. That anchor is the echo. And spending the echo on it is exactly what leaves the catheter free to check our work. Only now, split matched, level matched, pulse matched, everyone against non-invasive data, do we bring in the catheter. The model predicts a mean pressure of 45. The catheter measured 45. They agree. And because the catheter never touched the tuning, that agreement is a real validation, not a curve fit. That's the moment the model earns your trust. And a trusted model finally pays out. Now you can read the quantities you ran the CFD for in the first place, the ones no measurement gives you, wall shear stress, and how it flips direction over the cycle, the energy the flow dissipates, the pressure gradients, and the load the arteries throw back at the right ventricle. Same anatomy, same inflow, but the diseased Windkessel, stiffer and more resistant, drives a completely different field. That's a patient-specific model you can actually believe. That's all for this video.